Anyway, thank you, Brian. I've forgotten how dynamic a speaker you are, and I'm sitting back there and I'm thinking, okay, upscaling for geomechanics. Woo! Anyway, well, that's fantastic. The only thing I can say is that a couple of the slides that has been shown, that Brian had shown at the front end about population growth and stuff, and will be the front end of Thursday morning, as the introduction to the school and conversation. So now I'm going to return back. Giovanni, I'm going to do my best. I'm going to keep them alive for 2 talks on geomechanics, so we'll see how well we do, okay? Yeah, okay. And in fact, every year when you come to the summit, I'm always a bit in awe because I watch a lot of the presentations that have happened previously, and it's just amazing the amount of body of work that people do, and they review the kind of stuff that they're doing. And anyway, I just have this one slide. So what we're doing, we started in this relationship with the Energi Simulation family, pretty much on the left-hand side, sort of looking at where geomechanics fit into a whole bunch of things like in situ stresses, the relationships to how hydraulic properties change with geomechanical processes and things like that. And I think the one thing to point out now is that we are making the transition to much of the conversation that you've heard around the room today is this issue to geosafety, which is this subsurface assurance. It's a little bit agnostic to what we're injecting. Doesn't matter if it's CO2, if it's compressed air energy storage, if it's hydrogen, it doesn't really matter. It's looking at those issues that lead to ensuring that we are using that subsurface pore space appropriately, because everybody is looking to it as a solution space. Because many of you have seen hydrogen roadmaps and other roadmaps and everything else, and there's this huge conversation about what we're going to do, and then there's this little sentence at the end of the paragraph that says, yeah, no, we're going to take it and we're just going to inject it in the pore space. We have lots of underground pore space, and we're done, and then on they go. So really, that's what it's about. And I think Brian talked about this a little bit. In Alberta, there's a lot of activities. Many people have seen these maps before. The little purple, the blue areas and stuff like that are storage hubs that are underway. I think a massive undertaking that underpins exactly the kind of things that you heard from Brian. I think to support anything related to CCS, even in the hydrogen side of things. So the development of the hydrogen economy in Alberta, tied to a lot of developments that are happening in Fort Saskatchewan, for instance. You see the blue areas that are in and around Fort Saskatchewan. Well, this CO2 storage hub wasn't really about CO2. It's really about hydrogen. Like the hydrogen component in terms of it taking off was to make sure that the storage locations were there, sufficiently proven out at scale, ready to go commercially to handle the carbon management side of things. So there's lots of challenges there, though. And so in the context of the talk, what you'll see is that those are a lot of projects all sitting right beside each other, injecting at scale for a very long time at very large volumes. So if you take something like the Pathways project, the amount of megatons per year that they want to inject is basically, I'm going to go out on a limb, and I can't remember what it is, it's 3 to 4 times actually the current understanding of what large-scale CO2 injection is going to be in a subsurface. So it's a precedent-setting amount. And so when you look at that over the long term, and you look at these large-scale injection problems, the gigaton type stuff, you really have to worry about these issues with how you actually manage those simulations. I had a bit of a conversation with Eric this morning, or asked the question was, at scale, at these large scales, how do you deal with the properties from an upscaling context? The other thing has to do with the questions that are being asked for us from a regulatory point of view. If you take these documents, these are the kinds of things that are out in front of most of the people trying to develop these storage hubs. All of these things like fault, seismicity, CO2 plumes, pressure fronts, zones of weakness, those are all elements of how we have to deal with this upscaling component. And it's all what all those blue regions and those hubs have to worry about. So it's a challenge. If you look at the details, we have certain regulatory requirements, D56, D65, or D65 and others that define some of these things. A lot of the times you'll see here the words in red that you see at the very beginning talk about the extent of CO2 plumes, but in actual fact, which you actually saw a little bit from the conversations this morning, is that it had to do with the CO2 pressure plume. I think previously in a presentation, I think my rule of thumb is that almost all cases, if you were doing a simulation and you were looking at 25 years and you wanted to know how big the CO2 plume was, it's 2 kilometers away from the well. Doesn't matter what the relative permeability is, doesn't matter what it is, just pick a thing, it's that. But the pressure plume's a different monster. It can go for substantial distances. You saw, I think in Eric's presentation, for instance, these, in the Bunter Sandstone, like these, the regional extents of these pressure plumes can go quite some distance. So the question is that, you know, how would we get at trying to upscale those? You can't do a triaxial test on a little piece of rock this big and extrapolate to something that's 100 kilometers. It's just not going to work. So those are important questions. For us, there's a little bit of context, and I want to, because there's only so many things that can focus on, and so for the talk, I just chose to focus on this one thing and share with you a particular challenge that has to deal with a bit of upscaling related issues to this project, which is Aquastor, which I've talked about before. Eric had shown, I think Tosin was using some figures that showed some salt precipitation from this project. But Aquastor is tied to SaskPower's Boundary Dam project in southeastern Saskatchewan. It was one of the first coal-fired power plants that had a dedicated CO2 capture. Its primary motivation is to capture the CO2, sell it to Weyburn for CO2 enhanced oil recovery. But they needed buffer capacity, so they had to drill an injection well, and there's an observation well 150 meters away. And on average, you know, modest rates, 300, 400, 500 tons per day. It's not very large, maybe upwards of 600,000 tons now over the last 8 or 9 years. But there has been some really interesting learnings, and there's a particular challenge at the moment that relates to the upscaling challenge in geomechanics that I want to share with you a little bit. Just a plan view. It's a relatively modest site. You can see on the left side a little tiny wellhead. There's an offshoot from the main pipeline that comes across. Any time that Weyburn doesn't need the CO2 or there's a turnaround or something like that, CO2 is moved to the Aquastor well and injected. So there's lots of dynamics, up, down, backwards, sideways, shut in, all the rest of it. And so the geology, a little challenging. It's 3,300 meters deep, 115 degrees Celsius, very saline, 330 grams per liter, hypersaline. Deadwood Formation, which is essentially the same basal Cambrian sandstones in Alberta that most people want to inject in, that sit right above the Precambrian granites. The sort of analysis stuff that I think most people would be familiar with, you would take your data, build your models, petrophysics, maybe some a 3D seismic survey, we won't talk about any of that kind of stuff, and you'd build a model, do some simulations, you do some history matching. And so that's been done over the last 8 or 9 years, build the models, did our best. To look at it was relatively a small scale, but we have a particular challenge at the moment, and that's what I was going to chat a little bit about. And it's this monster. And so this particular monster relates to the identification of a structure on the top of the Precambrian that was seen initially. The sort of attribute plots that you see, I think this thing works now, is it? Yeah. So these attribute plots that you see off in the upper right-hand side, those were looked at initially in the processing the seismic, looked at and said, yeah, okay, there's a little bit of a structure there. And said, well, so when we initially started this, we looked at it as a flexure. It's a really modest thing. It doesn't have, in the classic sort of North Sea kind of thing of 60, 70, 80 meters of throw or anything like this. It's a modest, probably 4, 5, 6, 7, 8 kind of meters of relief on the surface of the Precambrian. Said, well, okay. And so off we went, drilled the wells, 2012, started injection in 2015. And what happened is that there was always this treatment of it being a flexure. Our joke is that we didn't use the other F word. We liked the flexure word, just not the other F word. Well, it turns out that there may be elements of the other F word in it. And is that Bruce Hart recently and some other people have started to take a look at it, and there's this gneiss anticline that goes down in the Williston Basin down into North Dakota, and the upper end of this gneiss anticline actually pops its head up right up into where Aquastor is, and it's the black lines that you see there are these remnants of fault structures that still exist in the Precambrian underneath the reservoir. And so a little bit of the context has said, well, okay, so then somebody would automatically look at us and said, well, why did you drill the wells there? Okay, mostly because, in many of you, when this kind of stuff happens, it's because that's where SAS Power said we could only drill the well. It was their land, that was the spot. If you wanted to have an Aquastore project, that was where you had to drill the well, so the well got drilled. And so we've been sort of looking at this for a while, and the reason for the upscaling part, and this, we'll see where this heads, is that this is not the 60-meter throw problem. And I think this is where a lot of the problems are going to exist in a lot of other people's projects when you look at this from a sort of a, does it reactivate or not, is that the deformation structure in these sort of modest, even fault flexure type structures on top of the Precambrian have led to a deformation structure through the deadwood that is not some major fault that goes up, up through. There's a deformation structure, a subtle, if you want to call it that goes up through the deadwood that in fact is actually modifying the way the CO2 is moving in the deadwood. And so when you look at it from time-lapse seismic, the plot you see in the middle, there's a bunch of other stuff, but just to focus your attention, this middle plot in the middle is that there's a series of time-lapse seismic surveys, and maybe just draw your attention to the pink outline. And the pink outline is the 4th monitor survey that was conducted, and that you notice that it has got this odd egg-shaped shape to it, and it's kind of truncated on the left-hand side. It's not the lovely circle. You fire up a simulation model, and if you don't put anything in, you get a lovely circle, and life is good, right? But in actual fact, the thing was growing in this truncated, so we realized, okay, well, hang on a second, there might be something related to where this deformation, the F thing, in the Precambrian. And so the challenge became, you could do the standard workflows that many in this room are way more expert at it than I am, seismic inversion, all the rest of it, do the properties, do the simulations, and you do a history match, you get on the far right-hand side, you do everything, you adjust permeabilities, you do all that stuff, and you can sort of match the seismic survey. The question, though, for us, and this relates a bit to where upscaling becomes a challenge for us, was we said, well, okay, we have no measurements at that fault location. There's no observation well, there's no fiber, there's no pressure gauge, there's no anything. And so we had postulated that there was this deformation structure in the deadwood that was leading to some capillary pressure kind of boundary, and we adjusted permeability, and we matched the structure of the weird plume. And we asked ourselves the question, what if there were other mechanisms that would lead to this shape? So Li Feng fired up some stuff, fired up codes, again, much like the experts in the room had done, sort of looked at issues around fracture permeabilities, flexure permeabilities, flexure dip, sorry, Li Feng had to use the right F word at that time, we didn't put in fault. Because in this particular case, was trying to model the effects of the flexure up into this deadwood zone. It wasn't a pure fault. But looked at all of those kinds of things, and what we found was that, interestingly enough, is that if pressure, not CO2, if pressure was going up that zone, you got exactly the same plume shape. So not a capillary pressure boundary inside the reservoir that was affecting the plume, but pressure was actually flowing up that zone due to enhanced permeability. You would get exactly the same interpretation of the plume shape. So, okay, well, so now what? So now you look at it and say, well, I don't have any measurements. Like my MMV program isn't monitoring that. So we've got some problems trying to figure out now at scale how to handle this stuff in this particular challenge. Simulations that were run in this particular scenario out another 22 years after history matching the left-hand side, at one certain rate you would never get above fracture pressure, but on an enhanced rate, if it ever came, I think the nameplate capacity in a boundary dam is about 3 I'm going to say, let's say 3,200 tons per day or something. It never really would take it. But even if you got to a modest 1,000 tons per day into this well, it would go above fracture pressure. So the question became for us is that if pressure, the one is really the one on the left-hand side is to look at here. And you can see that this doesn't end up being CO2 saturation. It's the pressure only that travels up that zone. So now why the upscaling issue? Like, how would we handle this at Aquastore? So this is to the meat of the talk, I guess, if you like. Standard fault reactivation work was done for this. The orientation of this fault structure, I mean, not the well constrained, unfortunately, but the orientation of the maximum horizontal stress was actually normal to this flexure structure. It wasn't the opposite direction, so it was reasonably high normal stresses as it was interpreted. You know, you do the things, the Moore circle, what delta P shifts over, touches, yada, yada, yada. A lot of experts in the room, you guys know all that stuff. And so the question was, will it or will it not reactivate? Do we really understand it appropriately? And so one of the things I wanted to share with you today is about this upscaling part. Lots of stuff you can do in upscaling, but to me the part that was interesting is whether we understood the upscaled component of in situ stress around this structure. And the part that was intriguing for me is this paper by Sanoki, 2021, and I've forgotten, I meant to write it down this morning. Anyway, I can't remember where I heard, but somebody had said, well, you know, I wonder if we should borrow some stuff that's happened in underground mining and underground environments. And this was done as a way to try and understand induced seismicity environments in underground hard rock mines. And what they did is Sanoki looked at it with the kind of standard modeling techniques that many people in this room utilize, not much different, you know, continuum, discontinuum modeling, all the rest of it. And the only way that they could get to explaining the microseismic events, in other words, the deformation in situ, was by generating a heterogeneous stress state that existed around this fault structure. It's not a simple Moore Coulomb, I'm going to shift it sideways environment. If you look at the kind of modeling that was required in order to try and actually match the microseismic events that was occurring in the underground mines, this was a point where if you look at these numbers, right in the fault core might be up at, you know, what if it's these numbers, but you can see what does that range from 10 to probably 10 to 30 MPa in and around the damage zone, the fault core, all of those zones. And so you needed to be able to upscale those parameters in order to appropriately model how this system was going to behave under fluid injection. And if all we were getting was pore pressure movement into that fault zone, then upscaling to this heterogeneous stress state becomes really important in order to understand whether we reactivate or not in the long term. And so there were some things, I mean, part of the talks today and others have been working on other stuff, and we have been working on this. We plan on, this is how we're going to try and do this. I mean, you can get some conclusions from folks if they think this would work or not. But this is how we're going to try and handle it. Abel, for his PhD thesis, he finished in 2023. I can't remember if I've shared this with the audience before, came up with this thing called a virtual rock mass approach. And what it was a technique where you would subdivide very heterogeneous. You could take something with 50 million fractures in it, for instance, subdivide it into these VRM voxels, test each of these voxels to recreate a compliance matrix. It was like this, and you would basically, oops, I guess the animation doesn't want to work. Cycle through a series of tests on this block that had the actual fracture sets in it from your interpretation, all the fractures, not a subset, and you would actually create an equivalent compliance matrix, and you know did some work. People do this in fracture modeling, but one of the things that he pointed out, and it's really this next slide, I'll skip along, was that's related to how this is upscaling work, is that generally, and again, wherever Heidi's sitting, if I get this wrong, yeah, okay, well, okay, be careful if I say this wrong. Most people, from a DFN upscaling perspective, will do what's seen in the red on the left-hand side. So I will have a particular DFN that I'm trying to upscale. I can't handle all of them. I'm going to upscale to a grid block scale that has some set of fractures in it. What I'm going to do is I'm going to use a technique. Sometimes they'll do it analytically with like an ODA method or others, and they'll do it on the left-hand side. But they will take the block and they will assume that the principal directions in which I'm going to analyze are Y, X, and Z, or if you want X, Y, and Z. And they will do the interpretation of the actual equivalent orthotropic properties for that orientation, which is the left-hand side in red. So you can see if I'm worried about deformation, I'm worried about stress transfer, I'm worried about how, I don't know, pick it, and Giovanni will share a bit more on issues around unconventionals, but are you thinking about stress transfers and all this other stuff in fractured medium? I would choose the values you see in red. The three orthotropic stiffness parameters are 2.2, 2 point something, something, something. The average is 2.2 gigapascals. But it turns out that because of the influence of the fractures in the compliance matrix, if you take that and rotate it to its principal planes, stiffness matters. It changes substantially, and you get the numbers in blue. Still the same block of fractures, except I get the numbers in blue. Now, all of a sudden, if I'm loading, and the loading is occurring now in one of the principal directions, the X-primed direction, I get a stiffness of 17 gigapascals, not 2. That changes everything. So when you think about that stress state around that fracture plane and that heterogeneous stress state, it makes a difference what decision you make here. So there was lots of stuff done. We had shown that when you do this and you rotate to principal planes, you can actually recreate fully distinct element responses from this. And we did some upscaling, and you can now take those equivalent orthotropic parameters that are rotated to the principal planes, and you can actually make some significant speed up in simulations by using a continuum model with these, and you can match discontinuums as opposed to the conventional orthotropic directions. Anyway, so it allowed you to do some stuff at scale. So in conclusion, a couple observations, and I do want to make sure I put my glasses on so I can read them in gory detail. I think that this upscaling issue for CCS, we chatted about it in the question to Eric, I think this issue about everybody moving to gigaton and having to upscale to parameters that exist in very large regional blocks that will include these kinds of effects is really important. Upscaling lithological and facies heterogeneity, you can do the same thing to upscale with lithological changes at scale. One of the things in CCS that's really kind of a key thing for well integrity and other things is this issue with thermal properties, and so how do you upscale to those? Fault reactivation, we've got a PhD student, Hedia, who's working away on seismic geomechanics because it has an impact on even how you might do the inversion. But permeability, deformation structures, all of those are going to play a role, and upscaling to those are going to be a challenge. I mean, I don't necessarily have all the answers. I don't have the answers for sure. So a bit of acknowledgement. I think one of the things I left this towards the end that I was a bit envious with folks is that I loved how they started off by advertising the posters, which I didn't do. So apologies to Gaith, Amir, Karen, Sandra. I should have done the sales pitch and AJ, the little posters. So apologize. Because they're doing some fantastic work, and the posters are next door. Energy Simulation sponsors over the years, Li Feng, Ali Reza, Jessica, and Abel for their work. And in particular, some of the stuff that's continuing. There's still some craziness happening at Aquastore. Maybe we'll talk about that next year. For PTRC and SAS Power and colleagues at Aquastore. So thanks very much.
Thank you, Dr. Chalaturnyk. Any questions from the floor here? I don't see any questions online. Okay, sorry, there's one.
It's Amir Hagi from Viridian. Thanks, Rick, for the presentation. With respect to the shape of the plume that you showed for the Aquastore, and comparing with the shape of the plume in the Quest. So my question is, do you see any relations between that shape and the directions of the maximum horizontal stress? Because some highlights from the GHGT conference from Sam Crever and Sally Benson presentation was incorporating the anisotropic capillary pressure relative permeability, and those are actually a function of stress. So what do you think about this?
Well, if you're a believer, and you looked at the right-hand side, which is the simulation that matched, that was mostly done with directional permeability derived from seismic inversion, AVO inversion.
Okay.
And that is aligned in the direction of sigma H min.
Okay.
So does that match what I tend to, the stuff that Sam Crever and stuff is showing is actually very powerful for, I would say very large scale simulation work and stuff like that. Aquastor is still pretty small scale. So I'm not entirely sure that it would be dominated by that. This is still,
The flag chair?
yeah,
the F
I
board,
think
yeah?
so. I think so.
Okay,
Yeah.
thank you.
Yeah.
Okay. Another question from Pat McCullough.
Hey, Rick.
Okay, Pat?
Great talk. I stress heterogeneity, and I'm just sort of wondering, you showed the example from a mining publication, and yes, 10, 15 sort of megapascal sort of variability, but in stratified rocks in this part of the world, we don't see that kind of variability when people do tests along a single horizontal or tests within a field, or at least I've not seen that. I just wonder, have you seen that in investigations where there's kind of a distribution, a PDF of minimum horizontal stress?
No. The part that caught me with that work was the detail to which they had microseismic information in the mine.
Okay.
Is they could not unravel its distribution and its sort of temporal evolution unless they gave it that type of stress variation up near the fault.
Right.
That was all. And so I
Yeah.
I wonder again about lovely little more Coulomb, sigma H min, sigma H max, and the thing, and I'm going to shift a more circle. When in actual fact, when I'm injecting at large pressures, I'm now at 10 megatons and 20 megatons of injection. Pore pressures going everywhere. Yeah, I'm not sure whether we should be thinking of it as very simple, or it should be starting to approach in these fault reactivation cases something like that, where these stress variations are complicated as you approach fault cores, as opposed to being.
Yeah, and that's a factor, of course. Yeah, stress is
That's all.
rotating near the fault. Yeah.
Yeah,
Okay, good.
that's all. Yeah.
Okay. Once again, thank you, Dr. Chalaturnyk, for your talk.
Thank you.